We hear all the time about these incredible AI models like ChatGPT, but behind all that software magic, there's a hidden world of actual physical hardware. So today, we're going to look past the famous GPU and uncover three crucial components that are, and I mean this, the real engine driving the whole AI revolution. Let's get into it. So let me ask you, what do you think is the biggest thing slowing down AI's progress? Is it the algorithms? Is it having enough data? Well, the answer is kind of surprising, and it's much more fundamental. See, the real bottleneck isn't our ability to compute information anymore, it's our ability to move it. To really wrap your head around just how big this problem is, look at this. Over the last 20 years or so, GPU processing power has absolutely exploded. We're talking a 60,000 times increase. But the memory that has to feed those GPUs, its speed has only gone up by 100 times. You see that? That massive, growing gap is the central crisis facing the entire AI industry right now. And this crisis, it actually has a name. They call it the memory wall. It's this bizarre situation where your multi-billion-dollar AI chip, literally one of the most powerful computers ever built, is forced to just wait. It's just sitting there, twiddling its digital thumbs, completely starved for data. It's like having a Formula One car that's stuck in rush hour traffic. This, right here, this is the villain of our story. To how in the world do we break through this wall? Well, today, we're going to look at three specialized hero technologies, each one designed to solve this crisis. We'll start with the need for pure speed, with something called HBM. Then we'll tackle the need for sheer space, with HBF. And finally, the need for connection, with CPO. And stick around, because at the end, we'll reveal the one company that, surprisingly, ties them all together. All right, first up is our hero of speed, high bandwidth memory, or HBM for short. Its entire reason for existing is to solve that data waiting problem by just force-feeding GPUs information at absolutely blistering speeds. So how does HBM pull this off? Well, think of it like this. Instead of a single-lane country road for data, HBM builds a massive, multi-lane superhighway. It literally stacks memory chips on top of each other like a skyscraper, and then drills thousands of tiny vertical channels through them. This creates this incredibly wide, high-speed path for data to just pour directly into the GPU. And make no mistake, this isn't some niche experimental tech. The demand is so massive that the market for HBM is projected to hit $100 billion by 2028. We're talking about a component that is absolutely fundamental to the future of AI. In fact, the supply for 2026 is already completely sold out. Naturally, the race to build this stuff is intense. Right now, SK Hynix is the undisputed king, commanding a huge 62% of the market. But you've got giants like Samsung and Micron fighting tooth and nail to catch up in this incredibly high-stakes game. Okay, but HBM has one big problem. It's incredibly fast, but it's also really small and expensive. Think of it like a high-performance single-car garage. That's great, but what happens when your AI model is the size of an aircraft carrier? You need a second hero, one that solves for space. And this is where high-bandwidth flash, or HBF, enters the picture. While HBM is all about pure speed, HBF is about pure capacity. The whole idea is to give you 8 to 16 times more storage space than HBM for a similar cost. It's about creating a vast new tier of memory where these enormous AI models can actually live. What's so clever about HBF is that it takes the flash technology we already have in our SSDs and just completely reimagines it. It's redesigned to act as what they call near memory. Basically, a huge, easily accessible swimming pool of data sitting right next to the processor, just ready to be used at a moment's notice. Now, this is a brand new field, but the big players are already making their moves. SanDisk came up with the original idea, and in a really smart move, they've partnered with the HBM leader SK Hynix to get the technology standardized. Meanwhile, you've got giants like Samsung, Kioxia, and Micron all scrambling to develop their own versions. Okay, so we've fed our GPU with HBM, we've given it room to think with HBF. But modern AI doesn't run on one GPU. It runs on tens of thousands, all working together. And now, guess what? The bottleneck has moved again. Now it's the physical connection between all of those thousands of chips. And the cost of this connection problem is just staggering. In a massive AI data center, just moving the data around can eat up to 20% of the facility's entire power budget. That's simply not sustainable. If we can't solve this, we can't build bigger AI. Period. The solution is a pretty radical shift. We have to go from electricity to light. CPO, or co-packaged optics, completely gets rid of the old electrical wires for moving data. Instead, it packages these tiny little optical engines, think miniature lasers and receivers, directly alongside the main networking chips. It literally creates a super efficient data highway made of light. And the results here are just dramatic. CPO today already cuts the power used per bit of data by 2/3 compared to the old way. And the future goal is to get that down to a 90% reduction. This is an absolute game changer. It's what makes building these massive interconnected AI clusters physically and, economically possible. So, there we have it, our three heroes. HBM for speed, HBF for space, and CPO for connection. On the surface, they seem like three totally separate solutions for three separate problems, but there's a surprising and incredibly critical thread that connects them all. So let's just quickly recap. We've got HBM, which breaks the bandwidth bottleneck. We've got HBF, which smashes the capacity limit. And we have CPO, which just dissolves the connectivity barrier. Three essential technologies, each one solving a fundamental pain point in building modern AI. And here's the twist. The common denominator, the one thing that all three of these technologies absolutely depend on, isn't some new material or a brilliant algorithm. It's the ability to physically assemble them. More specifically, they are all bottlenecked by the advanced packaging capabilities of a single company, TSMC. The real limit on AI's future might not be the GPUs themselves, but the supply of these three crucial support acts. I mean, the dependency is just undeniable. If you want to integrate HBM with a GPU, you need TSMC's CoWoS packaging platform. If you want to build CPO, you need their COUPE platform. And for the HBF modules of the future, you're going to need their SoISC integration. All roads lead back to one company's unique ability to physically put these incredibly complex systems together. And that really leaves us with a final, kind of provocative thought. We often think the AI race is all about who can write the smartest code. But as we've seen today, the future progress of AI might ultimately be decided by something much more tangible: the physical, microscopic art of packaging silicon.